I should have the same PowerPoint as you now as far as all of the right slides in it. All right, hopefully. So this is section 2, and it's just saying that kind of like what we've already seen when it gave the image of the world. It's saying, so just as the electric field is defined as the electric force per charge, the electric potential is defined as the electric potential energy per charge. And we'll see a comparison of that here in a little bit too, that I think is a little bit better. I wish they would have put that closer to this, but oh well. So you can see, like I said earlier, the closer that you are to the positive plate, if you have a positive charge, then you're going to have high potential energy. And then the closer you get to the negative, the lower potential energy you have. Kind of take this image and like rotate it that way to where it's standing up and the positives on top and the negatives on the bottom, and it would be just like gravitational potential energy. And then same thing for the negative charge. It would obviously have higher potential energy the closer it was to the negative plate. And electric potential is going to come up here soon in an equation, and potential is given the symbol V, and it's also given the unit voltage. Okay, so I actually kind of like that because electric potential has the same symbol as it does unit. So anyway, a volt is a joule per coulomb. Okay, so got some equations to give you. Okay, I thought I missed one, but I didn't. All right, so potentials do not have direction in space. They're just added just like any other scalar, and can be either positive or negative, and so must be added with their signs. And so the equation for potential energy for electricity is, we had one before that involves K, right? And it also involves the distance. But if we don't have that information, if we just have the electric potential, so we might have charge times voltage, or otherwise known as electric potential. Okay, which might be confusing because that U right there is electric potential energy. Okay, measured in joules, measured in volts. Okay, so try to keep that in place. All right, so potential difference, you can have a potential difference, which is the change of voltage. So just your final minus initial. And then the potential difference is the change in electric potential energy. So if you have a change of potential energy, then it's just Q times the change of voltage. Hopefully you guys can read my writing okay. All right, so electric field and potential difference. So for a positive charge, lower potential energies mean lower potential. So, you would basically just do like the voltage from, here to here, which would cause you to have a difference of potential energy as well. It would be like if we were looking at gravitational potential energy, the change of heights. Okay, so, height initial minus final or something, two different heights. Right, so electric field points in the direction of the decreasing voltage. So in a region where the electric field is 0, the potential is constant. And let me see here. Okay, we got another example. So a battery-powered lantern is switched on for 5 minutes. During this time, electrons with total charge of -8 times 10 to the second coulombs flow through a lamp, and 9,600 joules of electric potential energy, see, notice how it kind of follows it with energy, is converted to light and heat. Through what potential difference do the electrons move? All right, so this is wanting you to find potential difference. So whenever it just says potential, then it's basically wanting you to find V, okay? And we know our equation that involves charge and V is like this. And so we're actually just looking for the V. We're going to rearrange here. All right, so the potential energy that it gave us was 9,600. And you got to remember too that we're given that it was given this 9,600 joules divided by the charge, which was -8 times 10 to the second coulombs, which gives you a voltage of 12 volts, which is your potential difference. Okay? So potential due to a point charge. We've been given this equation. So like this, and I'm just doing the two charges. One might be really little point charge where the other one might be, larger or something. Just that's the same thing that it did with mass whenever we were doing the gravitational force. And therefore the electric potential at a distance from a point Q is, okay, so why is that? Because if you go back to our equation here, V is equal to our potential energy divided by Q. So V is equal to our potential energy here, right, divided by Q. So one of those is going to cancel, and that's where that comes in. I know, it's a lot of equations. Believe me, I know. All right, so example 17.4. So we've got another set of charges that it's given us coordinates to, and also what sign charges they are. It wants us to find the electric potential at A, just at A, due to the three charges. So Q1, Q2, Q3. And then we'll look at part B in a minute. Okay, so first off, if we were looking at just Q1 first, what is our R value? Okay, so how far away from A is Q? Just 2 centimeters. Okay, and then if we were looking at R2, so that's going to be Q2, right? That's this distance right here. I'm going to do that, by the way. Okay, so I've got an angle here. So how do you do it if it's at an angle? You're going to have to do the Pythagorean. So we've got 1 squared plus 1 squared, which is the square root of 2, which is 1.4 centimeters. Okay, and then we've got Q3. So all of this is to A, by the way. So we've got another situation where we're going to have to do the Pythagorean theorem. So we have 1 squared plus 2 squared, do the square root, and you get 2.2 centimeters. Okay, and the question actually said to find the electric potential at A due to the 3 charges. So whenever you have a multitude of charges, you just do the sum of them like you did kind of with the previous example that we had. Okay, but this just wants the potential, not the potential energy. So just voltage. Okay. So we're going to do our K. Okay, times our charge divided by R. So we've got, I'm going to just do like this, and then I'm going to put it in brackets like this. So we've got charge 1, which is 4 times 10 to the negative 6th coulombs divided by 0.02 meters. Remember, we had centimeters, so you want to make sure that you have that right. Plus charge 2, which is positive 2 times 10 to the negative 6th divided by our 0.014 meters, plus charge 3 now, which is negative. I was getting ready to put microcoulombs, times 10 to the negative 6 coulombs. Sorry, it's really late. I have to do things late because my children. Oh, this is crazy time, isn't it? And anyway, whenever you go to do the math on that, you should get plus 1.863 times 10 to the 6th volts. Okay? So if it says just potential difference for all different, multiple charges, you just add them up. Okay? And then part B actually said, there was a part B, and I have barely any room, so I don't know if I might have to erase something here. Part B said that a point charge that was negative 5 nanocoulombs moves from a great distance to point A. What is the change in potential energy? Okay, so this actually does say potential energy. So it is actually wanting us to find U, which is another symbol for potential energy. And so it gave us the value of the charge to be negative 5 nanocoulombs. And the voltage to be we just use what we had solved in part A. 1.863 times 10 to the 6th. And that gives you a negative 9.3 times 10 to the negative 3rd joules. Okay? All right. All right, I'm going to stop the video here.